Today we are going to discuss a very important topic of digital communication. So that is like you can say that it is a very important tool that is used to convert the analog communication into the digital signals. So the name of that is the pulse code modulation. So you can say that it is a tool that convert an analog signal to digital signal. And you know what is analog signal? So analog signal is that signal where the amplitude can take values of a continuous range, like the values of the amplitude remains continuous in an infinite range, while the digital signal means finite number of values. So now come to the block diagram of pulse code modulation. So it comprises main three blocks. The first one is a sampler, the second one is quantizer, and the third one is encoder. The message is always continuous, like this type of message. You have a continuous time message that is input to the sampler, and we know what is the sampler. Sampler is basically digitize, or you can say discretize the continuous time signal into the discretized signal. Like you can see this example, like this is continuous signal. When you give that continuous signal to the sampler, the output of the sampler is something like this. Like you are getting discrete values at a certain points. So and then you are ending up with this type of waveform. So the time interval between the samples, that is known as Ts. Ts is equals to 1 over Fs. So this is the time interval, or you can say Fs is the sampling frequency, which is equals to 2 multiplied by the modulating signal. So what the sampler does? Sampler discretize the x-axis, like it discretize the x-axis of or the continuous time of signal following the sampling theorem. So what is sampling theorem? That the sampling frequency should be equals to or greater than twice the modulating frequency, or you can say at least the sampling frequency to have a better or sufficient number of samples. The Fs should be equals to 2 times the Fm frequency, and you name it a Nyquist criteria, and you can say this is the sampling theorem. We have already discussed three different methods of sampling in our previous lecture. So if you want to understand or get more detail about the three methods of the sampling, that is ideal, natural and flat top sampling, you need to see our previous lecture about the sampling, and there we have already discussed in detail about each type of the sampling. So let's say some few sentence about each type. Like if it is ideal sampling, so it means that the impulses are present there. Like if the signal was continuous, and then you can say that this type of pulses are there after for the ideal sampling. But if it is natural sampling, so then you can say that the pulse with short width but varying amplitude. You can see that the pulses have a certain width. The pulses have a certain width and the amplitudes are varying. Like you can say these are the amplitudes of upper, and this is amplitude of lower. So the amplitude is varying and the pulses are short width. So the second type is flat top. So flat top uses a principle of some sample and hold, and in this pulses of short width with fixed amplitude. And secondly, you can say flat top name, so it means that the top is flat and the amplitude is fixed as well, but here you can see that the amplitude are varying. So here the amplitude is fixed, top is flat, so that is why the name was flat top. The second is the quantizer. So quantizer means that the process of measuring numerical values of the samples and giving them a table value in a suitable scale. Like you can say that this is like discretizing x-axis, but for the quantizer this is discretizing y-axis. So this is discretizing y-axis, like it is taking the values from the y-axis, constant or fixed amplitude or fixed level. And the step size, you can say it is 2 multiplied by mp divided by l. Mp is the maximum peak point and l is the number of levels for each value. So amplitude, you can say, vary from 0 to 1 volt for suppose. So, and then if we have an example of 3-bit symbols, suppose we have an example of 3-bit symbols, then we can calculate the level. So 2 raised to the power n, so you can write this general formula, 2 raised to the power n. L is equals to 2 raised to power n. So if we consider 3 bits, so we can say that L is equals to 2 raised to power 3, that is equals to 8. So it means that 8 levels. The second point is voltage difference in between samples. So what is the voltage difference between samples? So you divide the range of the voltage, so that we have done there. Range of voltage is 0 to 1, so that is equals to 1 volt, because 1 minus 0, the answer is 1 volt. So range of voltage divided by the number of levels. So in our example we have considered 8 level for 3 bits, so, and the range is 1 volt. So 1 divided by 8, the answer is 0.125 volt. Quantizing interval. So what is quantizing interval? Finite number of amplitudes is known as quantizing interval. So quantizing interval is the finite number of the amplitude, means that you are, like here if you see this example, so these are the samples and here you are dividing each sample or giving each sample a particular value, because here you can say this is continuous. So continuous mean you can have the values of 0.1, 2, you can have value 0.2, 3, you can have value maybe 2, 1. So this is continuous values, but so this is like fixed value. So you can, if you wanna write these values in this format, you can write it point like 1 and then 0.2 and then 0.2. So it means that you are rounding off, not a continuous value. So it means that you are rounding off the values. So there is a category of quantization. The first category is linear. So linear means the level of the interval will be finite and fixed. So level will always be fixed, like in our example. So the level, there are 8 levels and these are finite as well. Second example is non-linear. So in a non-linear, level of interval vary with respect to variations and it is not a constant. So it means that in this case L may have different values. This other thing is that there is a quantization distortion. So what is quantization distortion? Like sampled or quantized output results in quantization distortion, which is the difference between the sampled output and the quantized output. For example, you have a sampled output is 0.128 and you know the quantized output, like in our example the quantized output was 0.125 volt. So the quantized output was 0.125 volt. So in this case the error or the distortion will be equals to 0.128 minus 0.125. So the answer is 0.004. So this is the distortion. So you wanna reduce this distortion. So if you want to reduce this distortion, so you have to do something. So what you can do, you need to increase the number of levels. So it means that you have to increase L. So if you want to increase L, so it means that you need more. So you know L is equals to 2 raised to the power n, or you can say n is equals to log 2L. So n is directly proportional to the log of L. So if you increase L, so it means that n will be increased. So if n will be increased, so it means that more bits. So it means more bits. So it means that you need more bandwidth for transmissions. So this is also not that good. So there is a trade-off between the increase the number of level and the how many number of bits. You have to have a trade-off between these two values. So that trade-off is a bit rate and the bandwidth. How can you define the bit rate of a PCM? That is equal to n multiplied by the sampling frequency. So where n is the number of bits and fs is the sampling frequency. Second is the bandwidth. So bandwidth depends on the type of the encoding as well as on the bit rate, or you can say that the bandwidth can be equals to bit rate divided by 2. So that is why there is a trade-off between the bit rate and the number of levels, or the bandwidth, that how can you improve or how can you reduce the distortion level. So after the quantizer there is encoder. So encoder means you have to represent each level. So you have to represent each level with the number of bits. Like in our example, we said n is equals to 3. So it means that there is a total 8 bits. So you can represent each level. So for example, 2 raised to power 3. So it means that is equals to 8 bits. So if there is a 8 bits, so it means that you can write each level with the 8 bits. So 3, so suppose 1 0 1 0 1 0 and 1 0. So this combination will represent one level, and similarly so on, each combination will represent a separate level of the quantization. So this is the digital data, that you can say that the electrical waveform that can your computers or your devices can understand the things. So that is why you are converting the signals into a suitable pattern that can be transmitted from one place to another place or over a long distance. So this is also advantageous as well. So it means that there are many advantages to perform the PCM as well. There are a lot of other advantages as well, but we briefly point out few advantages. The first one is hardware implementation. So for the digital data, it is very easy, it is very easy to make a hardware. The second thing is that low error rate and high fidelity, because the noise immunity or the noise interference is very less for the digital communication as compared to the analog communication, because the nature of the noise is also analog. So that is why the digital formation is you can say that very low noise interference. The third point is easier and more efficient to multiplex. So multiplex is a very big advantage of the modulation. So in this case, if you are using digital data, so for the digital data you can easily and you can more efficiently multiplex your data. Fourth one is the reproduction. So reproduction, when you receive the data, you have to reproduct, or you have to retranslate, or you have to extract the information from the received data. So that reproduction is very easy if you are using the digital communication. So as there are some advantages, so there are some disadvantages as well. Like if you are using digital data, so it means that bandwidth requirement, as we have discussed before, that we need more bandwidth to reduce the quantization error. So that is why large bandwidth is required. We have already discussed that the noise or crosstalk is less, but on the other way, or on the other side, you can say that the attenuation is more. So it means that you have to use more and more regenerator. Like after some distance, you have to use regenerator, so that the regenerator can again amplify the pulses and can again retransmit the pulses. So after a few a small distance, you have to use regenerator. So that is why, because of attenuation. So less noise and crosstalk, but more attenuation. There are applications of PCM as well. The first one is the compact disc. The second one is the digital telephony. It can be useful for the digital telephony, and the last one is the digital audio application. So that's it. I hope you understand the pulse code modulation very well. Of course, we will continue our discussion in order to have a more detail about the pulse code modulation in our next lecture. But we have give more detail about the sampler and other related information in our previous lecture. But still, if you have any question, you are most welcome. You can write your question in the comment box, and please be in contact and write your comments so that we can improve the quality of the lectures. Thank you for watching the video.